So the picture that you see here is electrical tomography that we performed a couple of years ago during a European project, another one. And this is basically the result of an inversion, basically coming from the gathering of electrical resistivity data or electrical resistance, basically along the Andarax Delta River. So we buried a 3-kilometer long cables in the Andarax Delta River and then measured the resistances, then inverted for an electrical tomography. So I'm happy to see that Thijs talked, if you know the old joke, an exploration manager asks a geologist, an engineer, and a geophysicist what 2 + 2 is. The geologist would respond, well, between 3 and 5. The engineer would say, well, like 3.99, and the geophysicist would say, what do you want it to be? So I'm glad to hear that now I can replace the geophysicist by the hydrogeologist, actually. So anyway, so I'm gonna talk about how to resolve basically inverse problems. And inverse problems, so the talk is gonna be a little bit more technical. I apologize for that. I should be in actually last week in geophysics. So ill-posed problems, actually, definition comes from Jacques Adama in the 19th century, which basically said that an ill-posed problem is a problem whose solution is basically not unique or unstable or doesn't even exist. And you can see that when you invert magnetic data. I forgot the source of that. So this is basically a magnetic field that was measured on the field, and you can see that you can actually model it pretty much everything that you wanted. So here's the question mark. So he was basically saying that, well, solving ill-posed problem was pointless, and that there was no point we were doomed to fail as geophysicists. Then came in Tikhonov in the early 20th century, and he basically was trying to understand how geophysicists in Russia could actually get information from a diffusion or subfield, and it was actually ERT data to try to find some oil field. And Tikhonov basically had the idea of then inputting into the solution of inverse problems what we will see as a regularization term that will basically stabilize the solution. So if you take the definition of a simple linear forward problems, you can see that the data D that we'll measure in the field, we'll try to reproduce it with some forward problems. And that forward problem can be seen as the product between a matrix G, which would be actually our forward mapping, then the model M that we are trying to reconstruct, right? And often the dimension of G is going to be basically the number of parameters versus the number of data that you collect on the field. And this one typically it's not a square matrix, right? So you cannot invert it, basically. So the way that you can think about inverting it is solution of the least square problem is just left multiplied by the transpose of G. Then you end up with the so-called least square solution, which is this one. And because now this one is actually square, and you can actually invert for it. So you would have the solution of your inverse problems basically as GTG minus 1, GTD, right? And there you would have actually a solution. The only problem with that is that the condition number of this matrix now that you form is actually pretty large, so it makes the problem actually quite unstable. So what Tikhonov proposed is actually to stabilize this inversion, and we'll see how in a minute. So basically we went from not being doomed to solve an inverse problems to being able to capture, for example, here in 3D, the river infiltration into the groundwater in a time-lapse manner. So during the talk, I'll see if I manage to cover all of these points, but I will talk about least square solution, how to solve this type of problem using singular value decomposition. I will talk about the Tikhonov regularization and different algorithms that can be used to actually solve the minimization problems, Gauss-Newton, Leverbeck-Marquardt, and Occam. Some of you might already be familiar with that. And then probably jump to that if I'm being too slow, and illustrate you with some regularization, image appraisal, and joint hydrogeophysical inversion before I close with some take-home message. You can already guess what it is. Anyway, so the least square solution. So yeah, I've been watching games and being pretty nervous about this. Anyway, so what I've written here on the board is basically what is being stated here. So you basically cannot reproduce exactly your data. So what you have to do is to come up with some data residual, which is basically the difference between your observed data and your model data. And you're going to try to minimize this, and we call this an objective function or that will become later on a functional. So the way you can compare those two vectors, so your data and your model prediction, you typically use the LP norm, which is here, which is basically the sum of the, how do you say that in English? The 1 over p exponent. 1 over p of the sum of the residual exponent to the p. And if you take p equals to 2, it gives you the least square solution. If you take p equals to 1, it gives you the robust norm of the L1 norm. And if you take the robust norm, it's actually called robust because you can face, let's say, outliers in your data. It's actually, you suppose that your residual have a double exponential distribution, whereas if you take p equals to 2, you have the least square solution because you expect that your residual follow a Gaussian distribution. And so you should actually try to minimize that with respect to some tolerance delta that basically is going to be your error or your uncertainties into your data. So this side is ugly, but it's the singular value decomposition. So it's basically the singular value decomposition allows you to decompose any matrix, and we will take that matrix as basically the forward mapping, into 3 matrices, one of which is diagonal, containing singular values. The two other U and V, actually 2 orthonormal matrices, that one spans the data space, that's the U matrix. So the column of P spans the data space, and the columns of V spans the model space. And the cool thing about this singular value decomposition is that you can always find the pseudo-inverse. That is, you can always find the inversion of this matrix if you remove all the 0 singular values, basically. So you can always invert this diagonal matrix, and since those are orthonormal, you can basically invert for them by taking transpose. So having that in mind, it means that you can also build the solution of the inverse problems basically as the more Penrose inverse, as basically VP here, the inverse of SP times UTP times D, and that actually will be your solution of your linear inverse problems. And when you look at that solution, actually explicitly here, you can see that you form up the solution, your model here, is actually a linear combination of this term with the columns of the V, because they span actually the model space. So if you would look at V, it would be actually quite smooth. The first indexes of V would be smooth, and then if you go to a later stage, it will be more complex. And if you look at this particular term here, you see that the data D that we have is actually contaminated by some noise, right? Or some uncertainty, could be your measurement accuracy. And here, it's divided by those singular values. And basically, the single values, they are arranged in the matrix S such that they're really low values at the end, so that if you take this here term, you basically will propagate the error in your data in a large amount into the solution. So which means that the solution also can become unstable if you take all the singular values. So one way to solve the problems is actually to cut P to a certain P prime such that you have a stable solution. But it's not always easy to select. Oops, sorry. So if you would solve the inverse problem set, this is an example of vertical seismic profile. So you basically have the slowness as a function of the depth. And if you use the full SVD solution, then you see that if this is your smooth solution, then you have a quite unstable solution around it. The other nice thing about this tool, so the singular value decomposition, is that you can use it to compute the uncertainty around the estimated model, which is simply an error propagation using your pseudo-inverse here. And you can also compute the resolution matrix defined here basically by the matrix V. And basically, the resolution matrix should be close to identity if you have a perfect resolution. And the more it goes away from the identity matrix, the worse resolution your problem actually is. So this actually is nice in linear terms because you don't depend on your model parameters. It means that if you want to do some experimental design and see what would be the resolution of your next experiments, you can actually use the resolution matrix to do so. OK, so now we go back to Tikhonov. And basically what Tikhonov added to solving this normal equation problem, he transposed the problems as follows. You basically, now we're not trying only to minimize the data residual, but we're going to add an additional constraint that we put on the model itself, right? So you can formulate it actually 2 ways. Either you look for the minimum of the norm of your model, subject to your data residual being within certain limit, or you minimize your residual, subject that your model respect a certain criteria. The second one is more difficult to say because you don't know much about your model at first. So if you use the method of Lagrange multiplier, you basically end up with this thick enough type of solution, which is the regularization, where you find the data misfit plus this alpha square, which is the regularization parameter, times the, now we have a new terms in the objective function, which is a model constraint, right? And here, basically, it's the original formulation when you minimize the norm of your solution. For example, you minimize the resistivity that you find in your solution. But you see that basically the introduction of this new solution will stabilize the inverse, and you can see it here, because you see that we again have this linear combination of the columns of V, but now actually the 1 over S is tempered or is dampened by this S squared divided S squared plus alpha squared. So you basically will dampen the effect of those really low SI values. So those are called the filter factors. So they will, yeah.
Sorry, I don't know if I missed it. Was G non-self-adjoint matrix?
Sorry?
Was G a non-self-adjoint matrix?
Was it none?
Self-adjoint, non-modular matrix?
I didn't
You're
get it.
doing singular value decomposition of
Yeah.
U. So was it a non-self-adjoint matrix?
No, it's not. It's not. It's a positive definite matrix normally. Yeah. Well, I will have to check that though. Yeah. It's actually a question that I'm not sure I can answer. Yeah. But anyway, so one of the way you can actually go and add new information in your data is, so instead of having just M as a term that you want to minimize, you can also write it as LM, basically L, bringing more information to the solution of the problem. So here L, for example, takes the first derivative of the model. So if you would multiply it by the model here, you will see that you will now not only minimize the residual, but also the difference between the two models' parameters. So basically this will bring you the smoothness constraint solution that you might heard of if you've been doing, for example, ERT. And that can actually also be solved using the generalized singular value decomposition, which applies to both G and L. So basically, so as I was saying, you now have this alpha squared term, which is going to cause problems because now you have actually to choose for it. So the question is, what actually would be a criteria to actually choose for it? So there are different types of way you can actually do that. One is called the L curve. So if you put it on the axis here, and if you put basically those two norms here, if I'm going to put a really high value on the lambda, on the alpha here, all I'm going to do is I'm going to basically minimize the norm here that is on M, right? And the opposite, if I take a really low value for alpha, then I'm going to basically only minimize the data misfit. So I'm going to have this type of curve, right? So if I have, sorry, I'm curving. So if I have really high values of the alpha, my M is going to be minimized. So I'm going to have my M here. And the other way around, I'm going to have my GM minus D, sorry, here. So really low values of M for high values of alpha towards infinity, and here alpha towards to 0. And basically the L curve solution is trying to pick something that is of maximum curvature here, and that is just the choice that you make in terms of the selection of these alpha parameters. Okay, so we'll skip that and go back in a moment. So this is an example of L curve, again for our vertical seismic problem. You see that here the corner is actually well defined, but so for some of you who actually tried it already, sometimes the L curve might actually not be well defined because it's just an empirical way of doing things. It's not sure that you actually have a maximum curvature. And so if you do that, if you solve the problems now using this thick enough solution with this alpha square chosen according to the alpha criteria, you will find back this smooth model as a function of depth, which is actually what you wanted, since we wanted to reconstruct this guy. Yeah. So here. Okay, so that was what I wanted to show for the linear problem. For the nonlinear problem now here, consider problems of the form of D equals the, it's a function of M, so it's not we're not in the matrix form anymore, so we cannot invert it for it directly. So again, we're going to state the problems as a minimization problem. So we're going to try to basically minimize here the sum of the residual applied to the square. So it's going to be, again, the least squares solution. And basically, what we want to do is if you apply so if you compute the derivative of this function and you make it equals to 0, you end up with the Gauss-Newton methods, where you try to find here the derivative of the functional equals here a term where you have the second derivative of the functional and then the step that you're actually trying to look for. So here, the point of the method is to start. It's an iterative method, so you start by choosing the starting model. Then you want to compute an update to the model. Then you solve these equations for the update, and then you continue. You apply the update, and you then define some conversion criteria here. So the Gauss-Newton approximation basically approximates the second partial derivative with the product of the Jacobian, so the transpose of the Jacobian times the Jacobian. So that's basically the Gauss-Newton approach. And you solve this problem for delta MK, and you repeat it until you actually are satisfied with the solution. So you actually reach some conversion criteria. So if you look actually at the linear problems, you see that there are quite some similarity between the linear problem and the non-linear one. So the Jacobian actually is what it's going to cost you in terms of computing. So there are different ways of actually computing this Jacobian. Either you go for analytical expression if you can, find the differences, adjoint state methods, or you can choose some mesh adaptation to reduce it, the cost of the Jacobian, because it will depend on the number of data and the number of parameters. You can approximate or compress the Jacobian, or you can actually use now, well, GPU computation. Here it's just a slide that shows you, a figure that shows you, if you compute the Jacobian on a CPU and on different GPUs, that the cost is actually reduced a lot. So this is the time in seconds to actually compute the Jacobian. So, however, we have the same problems as we have here. If we just compute here this product, we try to invert this matrix, then we're going to face also some problems because this product can be closed in singularity. So Levenberg-Marquardt is a type of algorithm that tries to remove this singularity by basically adding here a term on the diagonal of the matrix so that you can actually invert it. And so you solve this Gauss-Newton, but with this augmented damping parameter, which is the lambda here, just on the diagonal to ensure the conversion basically to the of the algorithm. So the Levenberg-Marquardt methods can be seen as this. You choose an M0 here. You pick a lambda value which will be as small as possible, not to basically that minimize the misfit. You solve for the delta MK, you apply it, and then you start iterating, right? And then you will here, and you follow up your way through a minimum of the objective function. Of course, these methods are local search methods. So basically, you can end up being trapped in a local minimum. So there could be way, or you could not only accept downhill step, but if you think that you're not at a sufficient low level of the misfit, you can also accept uphill step to get out of basically of the minimum, and then trying to find a minimum that actually suits your data uncertainty. So different ways of saying that you're satisfied with the iterative procedure. Either basically you're close to the minimum, so delta f equals to 0, or you don't have any improvement in the successive models, or you don't have any improvement in terms of the residual. So it would be likely with those type of methods that you would be trapped in local minima. So if you don't want to be trapped in the local minima, you would need to use global search methods to account basically for the full uncertainty of the problems. So this is just an example of a Levenberg-Marquardt approach in Raman spectroscopy, where you basically here convolute the blue curve, which corresponds to different bandwidth, to basically try to fit the red curve here that you try to fit to the spectra. Another type of algorithm beyond Levenberg-Marquardt is the so-called Occam principle, which can be seen almost as a philosophy of rule of thumb. So as in geophysics, you would say, well, if you have some doubt, you just smooth everything out, right? So you basically make the image quite blurry. So we basically use Tikhonov regularization, and you say we want to basically minimize here for example, the spatial derivative of the model, subject to the fact that we respect the data misfit to a certain tolerance level, right? So this is quite different from, it depends on really the algorithm that you would use, but this is going to be trying to push the smoothness to the maximum while respecting a certain data misfit. So basically the update becomes this sort of long formula, but you can see some resemblance to what we have seen before. So you see you have the J plus lambda square LTL times here the JT and the D, which is basically the data residual augmented by here the Jacobian. So if you look at how it works in terms of the conversion of the algorithm, the idea here is that you pick up a starting model, which will already influence, so bias sort of your solution. And then you start your minimization procedure. Then you will end up in the area you basically think that you have an acceptable misfit. So actually any model you can actually stop there would actually be good. So if you take like a software, some of them would actually stop when you're there, so where you're below the misfit. But if you look Occam principle, what you will do is trying to find the smoothest acceptable model within the range of the solution. So that will sort of ensure you a sort of a unique solution. So if you look at how an inversion method will progress as a function of the iteration here, here we have basically 3 iteration steps. So the one in blue, the one in orange, and the one in gray. And within those iterations, you have sub-iterations. So basically here, so this is the regularization parameter. This is the error-weighted data RMS. And what we do here in the first iteration is we choose basically the lambda, so the regularization parameter that will minimize the data misfit, and then we take the step. So you see that you have to search for it, and then you take the step and you select the one that gives you the minimum RMS. So you take the update, and now you're below your error level, which is here 1. Or you actually, here it's the error-weighted data RMS. So because you're below your acceptable level, now we will start to re-increase the regularization parameter and basically to force the smoothness. So we will re-increase the smoothness here, and you basically, for that, you basically ramp up the lambda as you go with the iteration until you basically reach the level that you actually desire. So in that sense, the Occam principle really seeks the smoothest model as possible. Well, in terms of if you define, of course, the criteria as the smoothness. So a little bit of regularization freedom. So basically, the geophysicist replied, as I said in the beginning, which model do you want? So this is a bit what we're going to see now. So if you consider, for example, the case where you have access to borehole logs, and for example, you have access to some boundaries in your model, well, you could decide that what you're going to put in your regularization term is not a smoothness constraint or a minimum norm solution, is you could decouple the regularization to basically force, you can impose isotropic smoothing in some area, and you can force between, for example, 2 cells, a strong anisotropic ratio so that you ensure that you have some structural constraint, for example. So that can be done by entering in this matrix here, which can be decomposed in a weighting in the direction tangential, basically to the boundary, or normal to the boundary. So we'll put more weight into the tangential direction if you want to elongate the properties along this direction. And you can also add here a reference model, like if you know the value of the model at certain location. You could also have a borehole geophysical log, right? If you put an EM39 into a borehole log, you can have access, for example, to electrical conductivity values from 10 minutes, thanks. From it, you can actually compute, for example, a variogram and compute a covariance matrix, so spatial covariance matrix for it, which you can also impose then as a regularization parameter. Right? So there it means you will impose the range, here in this particular case, the vertical range, but you would then need to find some way to constrain basically the horizontal range. In this particular case, what we did in the following example is we had the vertical variogram, and we assume basically some horizontal ranges, or a ratio between the two. So that being said, if we now solve an inverse problems using different type of constraints, that's why I was saying regularization freedom, you will have, for example, all of these 8 solutions, which basically all fit the data to the same level, right? So all of these models would be acceptable. So now, of course, the solution is, okay, which one do you actually prefer, for example? So here's the smoothness constraint model. So this is using Occam's algorithm. You see that you can actually increase the smoothness a lot. So this is a seawater infiltration test, actually. Well, not test, but site at the Westhoek in Belgium. So here you have some unsaturated area. And here you have the seawater infiltration that comes here. And by using borehole logs, we know that we have a clay layer in between. So here you see that by exaggerating the smoothness, you see that basically we have this seawater infiltration that actually cannot go through the clay because it's an impervious layer that actually you just overestimate the size of it. If you take the geostatistical constraint, so where we here force the correlation, then you see here that you actually limit much more in depth the seawater infiltration. This is if you impose a homogeneous reference model, so you see that if you look at the difference between the smoothness constraint and this one, that you impose the value here at the bottom, which are different here. Here you actually don't see so much of a change. I will see it in the next slide here. It's a structural inversion where we impose the top layer to be the one here observing the clay. And here you basically impose the same one, but at the bottom. So you impose the bottom layer. Here you increase the weight on the reference model. So those two are the same, but you just put more weight on this, on this alpha term. So you see that you sort of squeeze the seawater infiltration a lot. And there you basically put 3 reference models. So it means that you put more deterministic information. So you see here that by putting more information in your system, by imposing it, you actually can twist the solution in certain areas, not in all areas, but in certain areas. And the question is, how do you actually validate that? So in this particular case, we had the opportunity to have the borehole information. So I won't go through all of them because I'm also going to run out of time. But here, basically, you see the EM39, which is this here plane line here. This is a smoothness constraint solution here. So you see that it basically reproduces in a gross fashion what we observe, but that we are not being able to retrieve actually the value that we retrieve at the bottom of the EM. If you look at the geostatistical solution here, the 4A here, which is this one, is the one that usually fits the best because, of course, the information that we entered is actually correct. If you look at the structural information that we impose, so by basically imposing a structure at some location, I will give you an example here. We see, where is it now? We see here, this is this dotted line, that you actually impose a double minimum, which is actually not physically there. So you basically impose a wrong constraint, you still fit your data, so you think your solution is good, but actually you introduce a bias which is wrong in your system. So it's sort of like a double-edged sword, so you have to be careful when you impose such a hard constraint not to actually obtain then a wrong solution. And if you don't have ground truth information, you won't be able to basically tell whether it's right or wrong. So to tell whether it's right or wrong, there exist different ways to actually assess an inverse model, one of which take advantage of the Tikhonov regularization. Yeah, I speak a lot about tomography because that's a lot of what I do, of course. So there's this depth of instigation index by Oldenburg and Lee in 1999, which basically is basically doing 2 inversion by imposing 2 reference models. And it's like a game of looking, okay, what is common between the models and what is the difference between the models. So here, where are we? So this is a smoothness constraint inversion. This is inversion with a reference model, which is more conductive. This is a reference model, an inversion with a reference model, which is more resistive here. So you see clearly that we have some discrepancy here at the bottom and that we have similar structure at the top. And basically the smoothness the DOI would basically look at the difference between the solution of the 2 inversions and then divided by the difference between the 2 reference models. So it would be effectively close to 0 when the 2 inversion reaches the same model, and close to 1 when basically they are away from it. So where you basically, your inverse model tends to go to your reference model. So it's a way to see whether the inversion is controlled, or the model, is controlled by your data, or if it's controlled by your constraint. So here you see here that we have a wide zone which is homogeneously close to 0, which is actually well resolved, and then when you walk away from it, it rapidly increases, and then you basically lose the information.
Excuse me?
Yeah.
The 0.2 is like a threshold we can consider, or just for the
No, that's a good question, actually. It's a difficult one. so basically, when you compute the DOI, the advantage of the DOI is that typically the region with low DOI are flat, and then it starts increasing rapidly. So they can easily put the threshold just based on this flatness ratio. But if you would compute another appraisal tools, which is, for example, the resolution or the sensitivity, you would basically have a continuous image. So this is the resolution matrix, which is an approximation of the resolution that is well defined for linear problems, and the cumulative sensitivity matrix. And in this case, it's actually quite difficult to actually put a threshold about it. 5 minutes, right? Okay, so uncertainty estimation. So Jeff will say a lot about this, so I won't discuss too much about it. So this is just a, again, in tomographic word, just to show you that this is a toy problem that we had. And this is basically the results of inversion, where we basically contaminated the same data set, synthetic data set. So with the 100 realization contaminated by some Gaussian noise, I think 3 or 5%. And so this is the means of all the inversion, so the deterministic inversion. And if you look at the linear data uncertainty, so if you look at basically the error propagation through the inverse problems into the image, you will see that you propagate your uncertainty close to the borehole where you have the high sensitivity. So if you have error in your data, it will basically propagate into the region which have the highest sensitivity. If you basically take all those solutions and you start looking at the nonlinear data uncertainty, so the full uncertainty, you see that you have the same effect. So you have also high uncertainty close to the borehole, but that you see also have a high uncertainty where you actually have your structure there. So that's where you have also some nonlinearity in your problem. So, right, I should actually conclude. How much time do I have left? 2 minutes. 2 minutes, okay, right. So 2 minutes. So this is another example of minimum gradient support. And this is basically was a tracer test that we did in fractured rock. And so the idea here is try to find a functional that actually could be adapted for time lapse and used to basically try to find a salt tracer in a restricted area in fractures, because it would just go through the fractures because the rock is so massive. So we basically use this functional, which is the minimum gradient support here, that is defined here. And basically the principle is that the contribution to the functional of this minimum gradient support can be understood if you look at this curve here, meaning that if you have high gradient, basically, if you change a little bit the gradient, you won't penalize, you won't change the penalty on the objective function. So basically, high gradient will be stable. If you are located in this area, basically, if you change a little bit the gradient, then you will penalize it. So I mean, everything there, all the gradient located there will be unstable. And then if you zoom in and you look at this part, then again, you will find some flat curve, and the low gradient will be stable. So what you actually build up is like piecewise continuous functions. And so our toy problem was basically trying to find a tracer that would go through a limited zone here. And so we benchmarked the approach using a numerical problem, so a simple forward-inverse approach. So this is what a smoothness constraint inversion would actually produce. So you know that something has gone through, but it's like a big potato. So if you benchmark it, so the difficulty part was that you can actually parameterize this function with beta value. And so the difficult part was actually to find here the beta value that actually would give you the correct images. So that's something that was not clear. So here what we tried to do is to look against the data RMS in time-lapse mode, and to see that basically we took the beta that yielded the lowest time-lapse data RMS, and this was this H1 value, and you see that it's actually the closest one to what we want to reconstruct. So this benchmarked the approach. And if you look at what happened instead of the optimization behavior, so this is again the same slide, so the first iteration and the second iteration, you see that at the first iteration, we directly are below the acceptable level that we actually define. And that after that, basically all what the inversion did is to push, basically this is the regularization parameter, so we basically pushed the regularization operator to have this really small anomaly, only this one small anomaly and nothing else elsewhere. Right? So this was actually applied on the field. Again here, and you see here, of course, there's more noise, so it's a bit more dirty, I would say. So here you see you tend to the smoothness constraint solution when you find the location of the tracer here. And this is actually our optimum G, so where we have this clear arrival of the tracer, and you see that it also corresponds to the minimum data misfit. And I see you getting up. I won't have the time to go through that one anyway, which actually probably the most interesting one. But So questions to take home. So what I wanted to say here is that, okay, there are plenty of algorithms to solve your inverse problems. That's going to be an issue. So once you've known if your problem is linear or nonlinear, you know what you're going to use. So here, what basically you have to pay attention to is that how you're going to quantify your data error or your data uncertainty, and how is that going to propagate basically into the resulting model. It's going to be quite important if you want to address the uncertainty just from the data propagation point of view. Objective function definition, you've seen that actually you can twist the model to arrive at basically I can show you what I want you to show, right? And so you have to be careful how you define your objective function depending on what either the objective is or what is actually the most appropriate way to do it with the information that you would have at hand. Then you have to be careful in the computation of the Jacobian if you use one of those gradient descent based methods, because this is going to be the most time consuming. And you will see that a lot of the time that when I talk to people or talk to students is that there's a lot of things to actually tweak. So there's here the lambda, the alpha, the type of regularization or the norm that you put on your data, the type of regularization, the reference model, and all those little parameters that makes the inverse problems actually not all the times easy to actually use, or you don't want to take it as a push button, and sometimes it can be used. How far can I trust my inverted and conceptual model? So that's the reason for which we developed those image appraisal tools. What type of uncertainty am I accounting for mainly, and should I look into other models? And I think this is basically a nice way towards Jeff's talk. And the last the question is the most important one, is Belgium really going to win the World Cup?
Is there, would you say, a trade-off of over-penalizing or over-ruling out, and then like missing high-frequency changes, or like over-damping, and then
is there a risk of basically getting rid of some anomalies if you penalize it too much? For example, if you try to stay too much towards your background model?
yeah, so how would you quantify this risk of information loss?
Well, basically, I think you have to either so there is clearly a risk if you impose a constraint. For example, if you try to minimize the changes between two images, right? You can dampen changes that actually exist and you wouldn't know about it. So that's actually a risk that you can actually take. So if you use those, you can actually adapt those DOI index approach or sensitivity approach to try to quantify that if you have the background model, and to basically see where you would have actually good resolution, so that you know that deterministically speaking you would resolve it, and where you actually are constrained by the information content that you put in as a constraint. So that actually is how you would adjust it. So you can see the DOI index that is defined for static. You can actually apply it also for the time-lapse mode. Yeah.
So for me, you didn't address one topic, is that you can tweak the whole thing with your mesh as well.
Yeah.
And how do you think, well, what do you think about the idea is having small cells where you're more sensitive or over-determined and stuff like, or
yeah,
really better, or?
Yeah, well, it will, from a computational cost, of course, it will matter a lot. Now, the good thing about the Occam type is, so for example, if you have a really small mesh because you want to be accurate, right, into your forward modeling approach, if you use the Occam, if you smooth the model, then you don't risk to have too many artifacts. So that's one way to see it, right? The other way to see it is that you could, for the forward problem, so when you compute the data misfit, you can actually have a really fine mesh, and when you compute the Jacobian, you can use a coarser mesh.
No, but what I meant is have to
Yeah.
not to have regular meshes, but refine the mesh where you think you're more sensitive, like at the borehole, because.
Yeah, you could do that, but then if you do that and if you don't regularize the problems close to that, then you will find all those small variations, which are basically going to be artifacts. So what you have to do if you do that is you have to add more dampening at those locations when you have those really fine mesh. Or you have to use singular removal technique, singularity removal techniques, yeah. Yeah, Andrea.
When we're talking about these non-iterative methods, I think even people that are taking inversion hears about this Jacobian.
Yeah.
And you show a lot of methods to compute it. So what is your position regarding this Jacobian computation, and how
Well, basically, the best would be to have the analytical expression, because then it's absolutely correct. Finite difference is probably too costly and also approximates it. So often the best would be the adjoint state methods. So perturbation theory applied to your problems. Yeah. Yeah, Ty.
Can you briefly describe how coupled hydrogeophysical inversion would be defined with these formal terms, and what its main advantages, disadvantages?
You mean this one? Yeah. So here, so the way we did it in this particular case, so it was a seawater intrusion case. So so here we're not trying to estimate our. So basically, we try to use ERT data to constrain a seawater intrusion problem, right? Because of the sensitivity to electrical conductivity. So here, so we use the hydrogeological model, so basically mainly with uncertainty on the hydraulic conductivity and the dispersivity. From that, we simulate basically the seawater intrusion, so simulated for 50 years. And we simulate on top of that the ERT data that we would collect on such a system. And you compare it with your observed data. Well, this was all done synthetically now, but Andrea will actually do that in her PhD. And we use the Leverberg Markov to basically minimize this objective function, and having as unknown at this time not only the hydraulic parameter, but also the petrophysical parameters here. And what came out of it is actually, it was working very well in actually homogeneous case or simple case. But if you step in, so this is how we threshold it, for example, ERT images. One other thing that came out of it is that you're first, of course, very much dependent on your conceptual model. Right, so it's all about the conceptual model in the end if you want to use this hydrogeophysical coupling model. But if you were to use your images or your geophysical images directly to invert for it, then if you don't account for this loss of resolution typically, so if you don't threshold your image with respect to the sensitivity or to the UI, then you would basically get, so this is an example of a prediction of the isolines, and this is just using the full ERT images, so you see that it works okay for the homogeneous model, but for heterogeneous models, those are actually the prediction by the, or true model. And those are the ones that we retrieve if you do this hydrogeophysical inversion, basically. So conceptual model, and then if you don't do that, if you still want to use the ERT images and not go for the full coupled one, then thresholding your images.